All right, so this video is going to be a quick introduction to binary logic. My name is E.J. Daigle, Dean of Robotics and Manufacturing here at Dunwoody College of Technology. I'm going to talk a little bit about why binary logic is important to you. First and foremost is that when we talk about PLCs or computers in general, any industrial computers, we no longer communicate using analog voice or video like we're doing here. We really communicate using ones and zeros. So the most important of all of these languages or all these number systems that we'll talk about today will be the binary number system. What is the binary number system? Well, it's kind of like anything that's binary, on or off, true or false, male or female. These are all binary things. That means there's two possible states. In the case of the binary number system, we only use the numbers 0 and 1. There are other number systems that are prevalent both in the world of PLCs, controls, microprocessors, microcontrollers. One of them is octal, and octal means 8, so we call that base 8. And you'll notice instead of using 0 and 1, I now get to use the characters 0 through 7. One of the interesting things to always think about when we're dealing with computers is 0 is a significant number. What that means is it's always included. We always start counting at 0. We don't start counting at 1, start counting at 0. The number system we're most familiar with is the decimal number system, or base 10, that uses the characters 0 through 9. And one that you may not be familiar with is the hexadecimal number system. Hexadecimal means base 16. In that case, we use all of the 0 through 9, just like the decimal, but then we have characters for A, B, C, D, E, and F, which represent the numbers 10, 11, 12, 13, 14, and 15. The hexadecimal number system is fairly prevalent. We use a lot with things like binary coded decimal, where we use a 7-segment display. You've seen these on like old school alarm clocks, that this would be the number 8. If I wanted to display the number 3, it would look like this, where it would light up these segments to display a number. Well, they wanted a way to also display perhaps larger characters. So maybe I wanted to display a B. B would actually look like this on a 7-segment display. And obviously a C would look like this, and a D would look like this. And you can see that I can now display, using just those 7 segments, numbers from 0 to 15 by using some of these letters. So again, part of the reason we do this, or why we concern ourselves with this, is the fact that computers utilize things like transistors to represent ones and zeros. So the majority of what's happening inside that PLC or that computer is a sequence of ones and zeros. Just imagine, let me go back to my slide here. Imagine a bunch of characters, 1, 0, 1, 1, 0, 1, 1. That string of characters means something to the computer. It's a sequence of ons and offs that are represented. Each one of those characters may be represented by a transistor inside of that computer. So there's a transistor inside of there that is either saturated or cut off, and that transistor represents a number. All right, so let's talk about the basics on converting numbers. The first one we'll talk about is converting a base 2 number. This is what we call binary, base 2. What you're going to do when you want to convert that and look at what that number means in decimal, we take the number 1, 1, 0, 1, and we're going to take each one of those individual characters, 1 times 2, that's the base, that's binary, to the power of 0. That's kind of my index. This is address 0, address 1, address 2, and address 3. I'm going to add that to 0 times 2 to the 1. I'm going to add that to, okay, that was 0 because of that 0. I'm going to add that to 1 times 2 squared. And then I'm going to add that to 1 times 2 cubed. So you can see how these work out now. So it's whatever the character is multiplied by the base raised to the power of the index or the address of that associated bit. So this being 0, 1, 2, 3, so on and so forth. And this could go up to many, many characters. 2 cubed is an 8, plus 2 squared is a 4, plus 2 to the 1 is going to be a 2, and then 2 to the 0, anything raised to the 0 power is a 1. So if I add those up, 8 plus 4 is 12, plus 2 is 14, plus 1 is 15. Some people also, so that's the answer here, this would be 15, and it'd be in base 10, or decimal. Typically when we express decimal, we don't have to show the base. Only when we're doing something other than decimal, we'll show the base. Some people also say, well, I call this the ones place, I call this the 2s, the 4s, and the 8s. So if I know that the 8 is on, then it's 8 plus 4, not plus 2, plus 1. So 8 plus 4 is 12, plus 1 is, again, hold on a second here. Where did we end up here? Oh, I screwed up here. So this is 0 times 2 to the 1 is actually a 0. Be careful there. 0 times 2 to the 1 is 0. So good thing I did a double check here. 0 times 2 to the 1. So it doesn't matter that 2 to the 1 is 2. If I multiply by 0, I get a 0. So this is not a 15. This is 8 plus 4 is 12. This actually is represented by the number 13. Okay. Going to the next slide, sometimes we have to go back. So now we're going to go from that decimal number back to binary. To do that, when we did this one, we multiplied by the base, and typically to undo multiplication, we would do division, or to undo division, we would do multiplication. So what we're going to do is we're going to take 23, and this time we're going to divide it by the base. So 23 divided by the binary base, not by 10, but by 2. So when I do 23 divided by 2, this is like old school, like 3rd or 4th grade math here. I know that 2 goes in there 11 times with a remainder of 1. So 11 times 2 is 22, plus 1 would be my remainder, gives me 23. Then I'm going to take that 11, I'm going to move it over here. 11 divided by 2 is going to be 5 with a remainder of 1. 5 times 2 is 10, plus I have 1 left. So I'm going to keep doing this until this number right here goes down to 0. So it's not there yet. 5 divided by 2 is 2 remainder 1. 2 divided by 2 is 1 remainder. 2 divided by 2 is 1 with a remainder of 0. And then finally, 1 divided by 2 is 0 with a remainder of 1. So it looks to me to convert binary then, all you have to do is to collect all these remainders. And you do them in reverse order. You start here and you go up. So I get 1, 0, 1, 1, 1, base 2. That's going to be my binary result. Now I'm going to show you something kind of neat here. If I wanted to check my math on either one of these, what I could do is I could go into my calculator tool on my computer, and instead of going to scientific, I'm going to go to programmer. And within the programmer, I can see that I can type in any number. So if I want to type in a decimal number, I'll just click on the decimal here. I type in 23. And I can see that the binary of 23 is 10. Let's look at it here. If I click on it, 10111, 10111. And if I go to my previous slide, where we were doing the other conversion in the other direction here, I can do the exact same thing. I can take a binary number. So if I click on binary and clear it, now notice when I click on binary, I only get 2 digits to use, 1 and 0. So now I'm going to type in 1101, 1101. And if I want to convert that to decimal, click on the decimal, and I can see that that's a 13. So I can indeed verify that that 15 was not correct, and that 13 is what I'm actually looking for. All right, so let's keep moving on here. Converting an octal number to decimal. So let's look at what that looks like. So again, octal is going to be now a base 8. Okay. So if I take that 457 and I want to convert that to decimal, I start out the exact same way. 4, 5, 7. So this is going to be 7 times the base raised to the index. So this would be the index 0, index 1, and index 2. So that's going to be 7 times 8 to the 0 plus 5 times 8 to the 1 plus 4 times 8 squared. So I can see how those come together pretty quick and easy. This one looks like it's going to be a little tricky here. 8 squared is 64, if that's right? 8 times 8 is 64. Times 4, so 64 and 64 is 128. Multiply that by 2, that gives me 4 of them. That sounds like that's 256. Plus 8 to the 1 is 8, times 5 is 40. 8 times the 0, 8 to the 0 is a 1, times 7 is 7. So 256, 296, sounds like 303. And just to make sure that we don't screw this up again, I'm going to go check my math here with my calculator again. I'm going to take 457 in octal, and I'm going to look at that in decimal, and I see it's 303. So it looks like we did that one correct. And again, same way. Now I'm going to go 23, but I'm going to go to octal this time. So in the previous example, again, I multiplied by the base here. Now I'm going to divide by the base. So I'm going to take 23, I'm going to divide it by 8. 23 divided by 8 sounds like 16, so that's 2 with a remainder of 7. Yep. And then I'm going to take that 2 over here, and 2 divided by 8 is 0 with a remainder of 2. So that's kind of the tricky one here, right? 8 doesn't go into 2 at all. So I get 0, but I do have that remainder of 2 left over. So it would appear to me that if I wrote these in reverse order again, I get 27 base 8. Keep those, and I'm going to go back into my calculator here while I can. 23 base 10, so I'll click on decimal, clear it out, type in 23. And if I click on octal, I get 27, so 27 base 8. So we verified those answers on those. All right, I won't go back to the calculator again. I don't think I need to anymore, but you guys can check my work if you want. So now we're going to do base 16 to decimal. So what I'm going to do this time is I'm going to take A, 20, and 3. So it's base 16, so it's going to be 3 times 16 to the 0. I'm going to add 2 times 16 to the 1. And I'm going to add A times 16 squared. Now we want to remember, when we're dealing with hexadecimal, we know we get the 0 through 9, but then we also get A, B, C, dot, 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 all the way to F, where these are going to represent 10, 11, 12, 13, 14, all the way up to 15 using letters. So when I think about this A, I'm actually thinking about 10 times 16 squared. Well, I know 16 squared is 256. Times 10 would be 2,560. 16 to the 1 is 16, times 2 is 32. Plus 16 to the 0 is 1, times 3 is 3. And I'm going to get 2,560, which is 2,592, 2,595, I believe. Said I might not use that calculator, but just so I don't screw up the video here, I'm going to go just do a double check on this. And I'm going to go to hex. And you'll notice when I clicked on hex, I actually got the A through F over here now too. So A, 23, 2,595 in decimal. So that worked out pretty nice. And we'll go to the last one here. So it's just a good review for you guys. 99 base 10 to hexadecimal. So 99. So again, on that previous one, we were multiplying by the base. So the index, the item multiplied by the base to the index. So again, this was base 0. Oops, sorry about that. Base 0, base 1, base 2, or excuse me, index 0, index 1, index 2. Now we're going to divide by the base. So 99 divided by 16. Let's see, 16, 32, 64, 96. So it sounds like 6. So it goes in there 6 times. Let me just check that. 16 times 6. I just want to screw that up. 36, 3. So 96 would be 6 of them. So I'll take 6 with a remainder of 3. I'll take that 6 over here, and I'll do 6 divided by 16. And I get 0 with a remainder of 6. And write that in reverse order again. I get 63 base 16. And just to do a double check on this one as well, we'll take, and I'll type in 99 in base 10. So we'll go to our decimal number here. We'll type in, 99 in base 10. And I see that's 63 in hex, and that matches up with my 63 in hexadecimal. So it's important to be able to know what the number systems are and how they work. That will become more important as we get further into the semester. For right now, it's a good introduction. One of the reasons, especially on the binary side, one of the reasons why it's a good introduction is the vast majority of what we're doing inside of a PLC or inside of any computer is we're dealing with memory locations. And memory locations can be stored in as clusters or as strings of binary data. So the binary data is going to be one of our most common things. So if I talk about binary or base 2, we know we can only represent zeros and ones. But we can do that using bits, bytes, words, doubles. We can use all these different things. And when we do that, what we say is we say that the bit is the smallest unit of data that we find in a computer system. It is just one element that can only be a 0 or 1, an on or off, a true or false, or a male or female, whatever we want to call it. In our case, it's always a 1 or a 0. It can only represent 2 values, 1 or 0. So a bit means one element, just one element, one little box over here. And what does that mean? Well, that means we can eventually start to cluster things together. So if I get a collection of 8 bits, 8 bits is equal to a byte. And the byte is one of the most common data structures used in modern day computing. The 8086 microprocessor, which is the foundation upon which modern computing was built, was a byte-based or 8-bit system. The old school Nintendo Entertainment System was an 8-bit system. The interesting thing about an 8-bit system is you get 256 unique combinations. And you wonder, well, where's that 256 come from? Well, you only have 2 states for your bit. It can be on or off, raised up to 8, the power of 8, because I can have 8 of them. So you can see over here where 1 byte has, I see my numbers are off here. This is address 7, this is address 6, 5, 4, 3, 2, 1, and 0. So just kind of ignore this mess down here. But I can see a collection of 8 bits strung together is what we call a byte. And if I take that 2, the base 2, and I say, you know what, I'm going to use base 2. I'm going to need a scientific calculator this time instead. And I take base 2 and I raise it to the power of 8. You'll notice that gives me 256 unique combinations as to how I can do this. And when I say 256 unique combinations, what we're really saying is, combination 1 would be if I had 8 zeros. This is one of the possible combinations. The next one would be 0, 0, 0, 0, 0, 0, 0, 1. Then it's going to go down all the way down to where it's going to finally get to 1, 1, 1, 1, 1, 1, 1. And you got to think about all the combinations. So this goes, so the next one here would be a 0, 0, 0, 0, 0, 0, 1, 0. So you can see how it's going to go. And I'm not going to write all 256 unique combinations for you, but that gives you an idea of what that would look like, is 256 unique combinations. So that would be our byte, 8 bits collected together. A word. The word is one of the most common units or memory structures used in PLC programming. It's a collection of 16 bits. You'll notice that the addressing of a word, the most significant bit is going to be bit 15. The least significant bit's address is going to be bit 7, or bit 0 rather. And so we always think about a word as being 16 bits. Well, we could also say 16 bits is 2 bytes. So we could say there's 2 bytes within a word. Absolutely. One of the interesting numbers, if you take not much more note than anything else, is I want you to note this number 32767. If we take 2 and raise it to the power of 16, let's take a look at what we get when we do that. So I go to my calculator here and I go 2 raised to the power of 16. I'm going to get 65,536. And 65,536 is the number of unique combinations. Now I'm not going to write out all the possible combinations. That would take me probably a year to write those out. But what I noticed, this 32767, is this would be like an unsigned, where I go from 0 to 65,536. I also, though, could sign that and have some of the values be negative and some of the values be positive, in which case I would go from negative 32,768 all the way up to a positive 32,767. And I bring that up is that these are important numbers. When we get into the world of PLCs, many of our PLCs are going to be 16-bit addressed, which means if I want to use a timer, a counter, or other data, even math data sometimes, integers and things, I'm going to be limited to this number range of negative 32,768 to positive 32,767. So sometimes people say, oh, does that mean I can only count 32,000 items? Well, no, it doesn't mean that you can only count 32,000 items, but it might mean that one individual counter is limited to 32,000 items. But there are some other things that we can do to count beyond 32,767. We can roll over. We could have nested or daisy chaining of things. So there's lots of things that we can do. So word, 16 bits in a word, 2 bytes, so on and so forth. And then the double. The double is a collection of 32 bits. Notice it addressed from 0 all the way up to 31. I'm not going to do the math on this one, but guess what? If you do 2 to the 32, you get a number that's 4294, 967, and 295. So there's 4.3 billion, roughly 4.3 billion unique combinations, and this would even take me longer to write out. It does bring up an interesting story. A number of years ago, I had a student that was at Best Buy looking at TVs, and he told me, came back and he told me it was just when these flat screen TVs were coming out, and he told me he was looking between two TVs, and one of the TVs said it had 32-bit color, and that 32-bit color TV was, it was pretty expensive at the time. It was like $1,500. And then he looked at another TV, and it had 4 billion colors. It's what it said, it's what it advertised. And he said, that one was like $1,800. And he said to me at the time, he goes, you know what? I went ahead and splurged and got the, for only $300, I got 4 billion colors instead of 32-bit. And I had to explain to him, guess what? 32-bit is 4 billion. So you got to be careful on that, right? So anyways, a double is another type of addressing system. And as we get into, we go from 16-bit to 32-bit, some of our newer computers and our newer PLCs will actually be 32-bit. What does that mean? Well, that means now a counter might count to 4 billion or half, plus or minus 2 billion, right? So I can go to negative 2 billion and positive 2 billion. But it gives you again an idea of why the number of characters or the size of the collection of bits is important to us. All right, Boolean Gates. Some of you may have taken a course in Boolean algebra or Boolean logic. This is kind of where all of this is heading. We talk about OR gates and AND gates and exclusive OR and NOR and NAND and inverters. You'll notice when we talk about these, I'm just going to talk about the OR for a second here. This is an input, this is an input, and then this is an output. So OR means this or this gives me that. AND would mean this and this gives me that. And a NOR would be neither this nor that would give me that. And a lot of these ones with the dots actually use this little inverter. And we don't have to have the inverter with the not symbol. We can actually do it with just these circles. So let's look at these individually. I think that'll help us a little bit more here. The AND gate. Let's look at this one first here. So if I look at the AND gate, let me draw right here. The AND gate, again, looked like this big letter D. That's how I remember it. AND looks like the letter D. And I have an input A, I have an input B, and I have an output Q. When we talk about an AND gate, again, Boolean logic says, well, this can be 1 or 0, 1 or 0, and 1 or 0. On or off, on or off, on or off. We use something called a truth table. A truth table lets me look at all the possible combinations as to how this thing can be put together. So I have A, B, and Q. Again, Q being the output. So if I look at all the possibilities, I could say, you know what? A is off, B is off. And in an AND gate, A and B need to be on to get an output. So if neither of them are on, I'm not going to get an output, so the output's going to be off. Again, where 0 represents off and 1 represents on. And if I get a 1 and a 0, again, I need both. I need both of these to be on. I'm going to get an output of 0. And if I get a 0 and a 1, I'm going to get an output of 0. The only way I'm going to get an output of 1 is if both of them are on, in which case I'm going to get an output of 1. Sometimes people ask me and say, well, what does this mean, AND gate? Well, imagine your car. You've got your keys installed in the ignition. You've got the door open. And if both of these things are true, I get an annoying alarm, a little buzzer alarm going ding, 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 ding. Why? Well, because the automobile manufacturer said if the keys are in and the door is open, we don't want you to lock your keys in the car, so we're going to sound this alarm. That's an example of an AND gate. If we go into the OR gate, a little bit different setup. The symbol changes a little bit. So this is one of the ways we'll know it's an OR gate. It gets curved right here, and then this part comes to a point like that. So this is your OR gate. There's your output, there's your A, there's your B. In the case of an OR gate, we say either or. So if A or B is true, we're going to get an output. So our truth table is going to look like this, where we say either one is going to give me an output. So if neither of them are on, I don't get an output. But if either one is on, so if one is on and the other one is not, I get an output. If this one's not on and this one is, I get an output because of either one. If both of them are on, I get an output. And so the example here I would say is like the fire alarm at Dunwoody. If I get a smoke detector, that turns on, or if I get a heat detector, then I get an alarm. So either one of these, this or this would set off the alarm. Or you might even say, well, if I have a 3-input OR gate, maybe I have a pull station, one of those pull stations that you're not supposed to pull, right? That could also give me an alarm. That would be a 3-input OR gate. So just another example. The inverter. The way the inverter is drawn is it looks like this. It usually looks like a triangle with a dot. And usually we have A, and then we usually have what's called A naught, or not A is what we would call it. Real simple on this, we'll call this A and Q because that's what we've been using. So if this is A and this is Q on our truth table, a 0 in gives me a 1 out, a 1 in gives me a 0 out. So all this really means is not. Whatever I had on the input, it's going to be the opposite on the output. It's kind of like the reciprocal of what we're looking at. 0 gives me a 1, 1 gives me a 0. The NAND gate. The NAND gate looks just like the AND gate. So if I draw the NAND gate, I'm going to start off with that big D again. The only difference is the NAND gate has this little dot, which is really an inverter. So that inverts is what that does. So here's my Q, here's my A, here's my B, here's my truth table, A, B, and Q. And in this case, treat it just like an AND gate, but invert the output. So normally a 0 and a 0 on an AND gate, I require both inputs to be true to get an output. So normally this would be a 0 on an AND gate, but I'm going to invert it to a 1. Normally on an AND gate, a 1 and a 0 gives me a 0 output because I require both of these to be true on an AND gate, but I'm going to invert it, so I'm going to get a 1. A 0 and a 1 would normally give me a 0, so it's going to give me a 1. And the only way an AND gate would normally give me a 1 is if I had a 1 and a 1, but in this case I'm going to invert it to a 0. So if I go back to my AND gate, you can see on my AND gate that these are 0, 0, 0, 1, and you can see on my NAND gate that they're the exact opposite, 1, 1, 1, 0. So just a NAND gate is like a negated AND gate. It's like taking your result and I want to say multiply it by -1. It's not really. It's like taking your result and just inverting it, giving me the opposite output instead of what I'm expecting. And the inverted OR gate, or the negated OR gate, would be the NOR gate. So I'm going to do the same thing here. I'm going to draw the OR gate. It's got that curve, it's got that point, and it's got that dot. And again, we'll have A, we'll have B, we'll have Q, and the truth table will be A, B, and Q. Now, in order to understand how the NOR gate works, of course, we've got to understand the OR gate. The OR gate said that any one, either or, will give me an output. So normally an OR gate would be 0, 1, 1, 1, because as soon as I see a 1, I get a 1 output. So normally I'm expecting 0, 1, 1, 1, 1. In this case, a 0, 0 on an OR gate would give me a 0 out, but I'm going to invert it. A 1 on an OR gate would give me a 1 out, but I'm going to invert it. A 1 on an OR gate would give me a 1 out, I'm going to invert it, and 2 1s would give me a 1 out, I'm going to invert that as well. So our negated OR gate, again, is going to look just like our OR gate, where we have 0, 1, 1, 1, but we're going to invert it to 1, 0, 0, 0. Okay? And then the exclusive OR gate. Let me go back for a second here. The exclusive OR gate looks a little bit funky. Looks kind of like this. It looks like an OR gate, but it's got this extra line. Kind of like that. That's the exclusive OR gate. So I have A, I have B, I have Q, and I know it's the exclusive OR gate because I can see that extra line on it. And for the exclusive OR gate, truth table, only slightly different. Exclusive means either or, but never both. So I can use A or I can use B, but I can't use two at the same time. I think of it like a motor. I can put my motor in forward, I could put my motor in reverse, but I cannot put my motor in both directions, right? That would not be allowed. So if you think about that, a 0 and a 0 on an OR gate would give me a 0. A 1 and a 0, that's okay because it's not both. It's going to give me a 1 output. A 0 and a 1 is going to give me a 1 output. The only difference between the exclusive OR and the OR is a 1 and a 1 will actually give me a 0 output. So I can't run the motor in both directions. I can't drive my car in forward and reverse at the same time. All right. And then some real quick truth tables here. One of the things you'll see in the worksheet is I'll ask you to do some basic truth tables. So when we talk about AND gates and OR gates and NAND gates and NOR gates, we can actually do these with logic. These could be switches or they could be contacts. In this case, this is what we call a ladder diagram. And what I'll say is, in this case, if I have a 0 and a 0, think I've got power right here, right? And I've got my return right here. If I'm routing current through here and I get to here, okay, if this is open, 0 and a 0, so this is not closed, I can't route power to my output. If I call this my output right here, I'm not going to get an output out, right? If this is open, even if this is closed, right? Even if this is closed right now, if I close this real quick, it doesn't matter because I can't get power through A, can I? So even if I've got a 0 on A and B is closed, I'm still going to get a 0 output. Then, let me see if I can grab my eraser here real quick. Pointer, eraser. The other option then would be if I had A on, let's say I turned A on, but not B. Well, now I can get power all the way to B. But if B isn't on, I'm not going to get anything to the output. As soon as I turn B on, I'm now going to get an output. I now get current flow, and I get a 1. And now you got to ask yourself, what gate does that represent? Well, let's think here. 0, 0, 0, 1. So if both of them are on, this and this have to be on. That must represent an AND gate. Looks pretty good. And then we'll go over here and take a look at this one. Now we've put these two in parallel. We've also put a control relay. Think about a control relay real quick. The way a control relay works is the figure is drawn in the de-energized state, meaning the coil is shown in a de-energized state, which means this is the normal condition for the contact. So when the coil is de-energized, this contact is closed. And when the coil energizes, this contact will open. So a 0 and a 0 right now means that the coil is going to be de-energized. If it's de-energized, then power is going to route through this normally closed contact, and I'm going to get an output. If I energize B, now what's going to happen is the coil is going to energize. As soon as the coil energizes, this contact that's associated with it is going to change states. It's going to open up. When it opens up, that's going to turn off the output. It'd be the same if I energized A. If I energized only A, I still would energize this coil, and that would open up the contact, and I would get a 0 output. And if I energize both like I have it drawn right now, obviously the coil is energized, which means the contact opened up, and I get a 0. Now you got to think about which one is this. Well, I remember the OR gate said any 1 would give me a 1 output, and 2 zeros would give me a 0 output. Well, this looks like the exact opposite of that. So this looks to me like a NOR gate. And as we get further into this, you'll understand what these normally closed and normally open contacts, and in the world of Allen Bradley, we like to call them examine if closed and examine if opened. So there's all kinds of things that we'll get into a little deeper. But I hope for, at least for this case, this will help you guys get through worksheet 1, and hopefully help you with the basics of what we're looking to cover here, which is Boolean logic.